My name is Nashir John Mohammed. I'm an undergraduate senior studying computer science, and today I'm presenting Closing the Generalization Gap of Cross-Silo Federated Medical Image Segmentation. The authors are primarily from NVIDIA. The exceptions are the first author, who is studying at University of Pittsburgh and was interning at NVIDIA when the work was performed, Pengfei Guo from Johns Hopkins University, and Huang from University of Pittsburgh. Interestingly, these authors have worked on many other papers that we've discussed in class, like UNetter, SWIN UNetter, and self-supervised pre-training of SWIN transformers. So I thought that was an interesting connection. So as we all know, deep learning models have shown success on various computer vision tasks in recent years, but training these models to generalize well on unseen test data requires a lot of data. And in the medical setting, a single institution may not always have enough data for the medical image segmentation task due to the expensive procedure of collecting data and annotating it with expert labels. So since it's hard to train on data from a single institution, we might not have a good model. One solution is to collect data from many institutions and aggregate it and train a central model. But this could violate patient privacy concerns. So gathering and centralizing data is something we don't want to do. Could use vanilla distributed training, but some works have shown that this is not like the most efficient because the communication complexity, and there are also privacy concerns because the leaked gradient can be used to recover pixel level images. So the solution, as we've talked a bit about in class, is federated learning. It seeks to solve all these problems: insufficient data, data privacy, and training efficiency. So I'll cover a bit of review on federated learning in a few slides. But the key idea of this work is that they seek to reduce the client drift that often happens in the federated learning setting, and they propose a method to address this issue. So in this work, as I said, the authors develop a method to get rid of the client drift issue for the medical image segmentation task specifically. But their framework could be used for other supervised learning tasks. It's not specific to medical image segmentation. So the authors propose to train, rather than training a global model that fits all the client's data distribution, they propose to produce personalized models to fit different data distributions well. And they also develop a novel model selector to decide the closest model for the data distribution of an unseen test data. So before diving into the approach, I'll talk about some background related work. As we've talked about, federated learning is a distributed machine learning scheme where many clients collaboratively train a global model under the coordination of a central server. They train their models using private local data and upload model updates to the server. There are two main types of federated learning: cross-device and cross-silo. There are other distinctions, but this is the one that is relevant to this paper. So in cross-device, clients are things like cell phones, edge devices, small devices, and each client is likely to have a relatively small amount of local data. So for cross-device to succeed, it needs a large number, millions more to participate in training. But in cross-silo, clients are typically companies or organizations. So it's relevant to the medical setting. Hospitals are considered one of the clients. This figure on the right side of the slides shows a figure from a paper called Scaffold, and it highlights the client drift issue where the local models wants to overfit to their local objective and drift, which is shown by the orange squares, and they drift away from the true optimum, which is the blue squares. So this slide has a lot of text on it, but the summary is that it shows two baseline algorithms used in federated learning, which we covered both in class. The one on the left is federated averaging. The right is FedProx, and the bottom right shows a figure from Scaffold again, which proposes their solution to the client drift issue. So the left, very quickly, just so we're all on the same page, I'll review federated averaging. So the algorithm initializes a global model, and then for a specified number of rounds, repeats the following. It selects a random subset of the clients, and for each client in parallel, it sends a copy of the global model, trains on the client's local data, just using simple stochastic gradient descent, and returns the local updated model to the server. And then a new global model is computed based on the weighted average of the resulting K-client models from that round of training. And the weight for the client model K is given by the proportion of training samples. And inference with federated averaging simply uses the global model for each client. And federated prox basically seeks to address the client drift issue in a sense, because data in the federated setting is often not IID, which stands for independent identically distributed. So it's not always true that all the variables have the same probability distribution and mutually independent. Different hospitals may have different disease data and because of the demographics of their patients. So it's definitely relevant in this setting. So fedprox handles this by adding a proximal term to the loss function that restricts local updates to be closer to the global model, which is similar to the proposed personalization method, which keeps the personalized methods from drifting too much in this work. Yeah, so as I mentioned before, this work focuses on the medical image segmentation task, but I believe it can be applied to any supervised learning task. So I'll just really quickly review segmentation on this slide. Given some input image, we want to identify something maybe malignant in the image and output a segmentation map as an image. And the authors evaluate their approach using DICE. The idea of DICE is that if two images have perfect overlap, the score will be 1. And if there's no overlap, the score will be 0. So a higher score is better. These are the models used by the authors in this work. The left is VGG, which is just a typical convolutional neural network. And the right shows the 2D UNet, which we also covered in class. So yeah, these are the main components of the approach. The authors introduce a framework for a personalized model. I discuss how they train their model selector, cover their personalization method and the new objective, talk about a convergence analysis that they do, go over their training and inference algorithms, and talk about their datasets, experiments, and results. So this slide shows all the main parts of the architecture. At the top, you see the model selector, which based on the input data distribution selects whether to use the global model or one of the personalized models. The global model is used when the confidence on the data distribution matching another is not high enough, and each of the personalized models is trained on local data from client K. And the model architecture for the global models and the personalized model is the same. So yeah, so they define something called a supermodel, which is this tuple of the global model, the set of K client models, and the model selector. So yeah, the goal of the model selector, as I said, is to determine the best match, best client, or best model to use. If the test data is very similar to the client J's test data, we should use model J. So they explain 3 approaches. The first is the naive one to give us an idea of just basically what was trying to be done. And so they say that if we have the trained global and personalized models, maybe you train them using federated averaging or whatever, you do extra training rounds to train the model selector. And the way you do that is that you ensemble the outputs from each of the models. And to compute this term on the right of the slide, H equals, sorry, I should back up. I didn't clearly explain the output of the model selector. It's a vector of K plus 1 elements, 0 corresponding to the global model and the other K corresponding to the K client models. So the model selector outputs that vector YS. So that's what we want to learn in this process. So going back to where I was, we want to compute this H equal to the weighted sum of each client output times the weight from the model selector. And then we can compute the loss between the output we're expecting and this H that we computed and use that to update the model selector via federated averaging. So we want to learn some y s hat that minimizes this difference between our computed output and the true output. So this has a couple problems. It's hard to train this model to learn this, and it incurs extra communication costs after training. So approach 2 aims to solve the difficulty with the training. This computes the difference between the output of each model and the output from the individual client, and sets an index of a one-hot encoded vector. So one index is 1 and all the others are zeros, based on the choice of k that minimizes this difference between the output and the output from the client. And once we have that, we can compute the cross entropy loss to update the model selector. So this still requires extra training rounds after we have trained the personalized models, because it requires we have a personalized model before we can learn this. So the third approach, oops, there's a typo on the slide, sorry. Third approach is a type of sort of a heuristic. They realized that when they have data from clients K that they're training on, it's most likely that model K is going to be the best generalizing on that data. So they simply set the index of the model selector one-hot vector based on that client index. So this can be done in parallel with the other training, because it doesn't depend on having a trained personalized model or a trained global model. So it's easier to learn. It's very clear what the model selector should output, and it gets rid of the communication rounds after training. So here I show their proposed optimization method, their new objective method, and how they train their personalized models. Yes, okay. So on the left top here, you see WK star, and this is this choice of model weights that minimizes the loss on client K's local data. So this local WK star might not generalize well due to lack of local training data. And so one solution that others have explored is model interpolation, shown on the right side of the slide. And what this does is it interpolates between the global and the local model based on this mixing coefficient lambda. A lambda close to 1 means using mostly the local model, and a lambda closer to 0 means mostly using the global model. Yeah, the problem, the problem with this is that it creates a dependency on the global model during training. So if the global model isn't yet very performant, then that's going to negatively affect the training here. So the authors propose something that doesn't depend on the global model. They have this new objective function. I won't go too into the specifics of it, but the idea is that, like I said, it avoids the global model, and it is what's the word I'm looking for? An explicit objective function that they can optimize to learn their personalized models for each model. And the bottom shows their personalization method. It's called soft pull. And one trick that the authors use during training is they replace this WPK with simply the local optimum at each client. And so you'll note that at the bottom, lambda is chosen to be in the range of 1/k and 1. And if you plug in 1/k, you'll see that each of these coefficients is 1/k, and that just simply reduces to Fed average with the hard averaging. So I'm going to refer you to the paper for more details on the convergence analysis, but this shows, based on the 3 assumptions on the left-hand side, which the authors claim are commonly used in the federated learning literature, that they can do this analysis on the right to show the convergence rates and the convergence error. So I'll just mention 2 takeaways. Excuse me, 2 takeaways. When the data similarity is low among clients, a larger lambda should be used to ensure the convergence rate. Remember that a larger lambda places more emphasis on local data. And so in non-IID settings, it's intuitive to use a larger lambda because the client has less learned from other clients. So you'll see, as you increase that lambda, then convergence error decreases. Sorry, what I said was right. As you decrease lambda, the convergence error increases, but that does not mean worse generalization because they don't want to overfit local data. So what the authors do is they empirically tune lambda in one of their ablation studies, which I'll show later. So this algorithm, as you can see, is very similar to federated average. The key differences are the training of the personalized model, the model selector, and the addition of the soft pull term in the aggregation of personalized model K here on line 16. So we go through train the global model, train the personalized model. This is on each client, and train the model selector. And then we aggregate those after. So it's very similar. The main difference here is that during inference, we use the model selector to determine the index of client that we're going to use. And we have this threshold gamma that's used to determine whether or not we use the global model or one of the personalized models. If our confidence is not high enough, this threshold, then we simply use the global model. I mean, yeah, that's right. I also mentioned on the previous slides, there were 3 approaches for training a model selector. The naive approach with the ensemble, FedSM extra, which uses extra training rounds, and FedSM, which is shown here. There's an appendix to the paper that describes the training and inference algorithms for FedSM extra, but again, I'll refer you to the paper for those. So the authors use 2 data sets, and what they do is they have a specific data set. They use 2 tasks, and for each task, they have a specific data set for each client so that we can enforce, some heterogeneity in the data. And this is just a summary slide showing the 2 data sets they use. You can see that on the left, there's lower data similarity between these images, different sizes, lighting, colors, features. And on the right, there's more similarity, and most of the difference comes from the lighting. So the left is the retinal data set, and the right is the prostate data set. Yeah, so the authors compare FedSM and FedSM extra with a few baselines, centralized training, which is just aggregating all the data and training a centralized model, which is the upper bound, but is prohibited in FL. We can't do that due to the issues raised on the first slide. Local training on a single client, which is not shown in this convergence plot. FedAv, FedProx, which we discussed, and Scaffold, which was the approach that uses, I didn't discuss it too much, but it's one of the alternate approaches that reduces client drift. So as you can see from this slide, FedSM converges to the highest value of the options. This slide also shows the training and experiment details, the models they used, the train validation test split, all those things. Yeah. And again, you'll notice that gamma was empirically tuned, which is shown later. So here's a table showing the test dice coefficient on the retinal data set. And you can see that the bold numbers show the top 2 performing federated average approaches. You'll notice that the centralized training sometimes has higher accuracy, but again, that's prohibited. So we just compare the federated learning approaches. Here, you'll see that for the most part, the approaches work the best. There's one instance where FedProx outperforms FedM extra and FedSM. One thing I thought was interesting on the previous slide is that in the setting with more non-IID, FedProx does not outperform FedAverage, which confused me because I would think that it would handle the situation better. So maybe some people have thoughts on that at the end of the presentation. Okay, and this is one of their studies where they validate the performance of the model selector. They leave one client out of training, and they see when they introduce that during the inference, what the most likely model to be selected by the model selector is. And you can see that in general, the performance is pretty good, except for they drop out client 5. The top table shows when they set the threshold gamma that indicates whether or not to use the global model to 0. So you can see the global model is never picked here, and it's forced to pick one of the personalized models. in the bottom table, they allow any gamma, the best gamma, and you can see that the dice scores are better. Is that true? Wait. Yeah, you can see that the dice scores are better here. For example, in client 5, the accuracy is worse. And you can see again that the global model is in fact used for these inferences. This slide shows a TSNE plot, and TSNE is a form of dimensionality reduction. I can't remember if we discussed it in class, but the authors use it to show that the model selector is learning features that clearly delineate the data from each client model. So when the model selector reads in client data from client X, it takes those features and reduces them to this 2D space. And you can see that the features are, for the most part, clearly separated, though there are instances like here and here where client data is mixed in with the others. But overall, this slide does show that the model selector did learn how to differentiate between the different clients' data. And these are two of their studies, the like ablation studies. The top table shows the influence of the lambda mixing coefficient on the dice score. They found empirically that 0.7 was best for the retinal task, and they didn't have a table showing the results, but they claimed that 0.3 was the best for the prostate data task. And the table at the bottom simply compares soft pull to other personalization methods. And you can see that soft pull does set the state of the art on the dice score for this task. This is just a qualitative visual comparison of the results on the retinal data set. The green line is the retinal disc segmentation, and the blue line is the CLEP segmentation. So you can see that the ground truth and the FedSM are very similar. It's hard to see visually what the differences are, and you can validate that by looking at the high performance. Some of these others are, not as great. This shows the results on the prostate dataset task, and again, the ground truth and FedSM look very similar. So really good results here. So some strengths. I really liked that the authors highlight the strengths and weaknesses of their approaches when they are describing their training and inference algorithm. For FedSM, they mentioned that scaffold has a better communication complexity because it doesn't have to transfer over the personalized model weights. I also liked when they were describing their model selector, they walked through the approaches that led them to the heuristic of just selecting the index of the local client. I thought that was nice, and I don't see that often. So that was something interesting that set it apart. I liked their ablation studies. It was clear the effects of their proposed method on the performance. The code is open source. The authors did a great job with their notation. I was never confused about what different symbols meant. Their convergence analysis is very thorough. They have 3 pages or so in the appendix describing the convergence of FedSM extra. Great experimental evaluation, though, and they did evaluate on 2 datasets, but I'll talk about weaknesses on the next slide. TSNE, to show the quality of the learned features, was very nice. They introduced a new framework, and they set the state of the art for the test to the best of my knowledge. So some weaknesses, just a couple places there were small typos. I mentioned one example, but that doesn't detract much. Like I pointed out in the slides on the table showing the performance, I thought it was interesting that FedProx performed worse than Fed average. But I'm not an expert on federated learning, so that's just something I want to point out. At first glance, the system architecture diagram was confusing. I'll go back to that really quickly. Looking at this at first, I thought it was unclear that they didn't specify what models were used, what the shape of these feature maps and stuff were, but the proposed model, the models used in the framework are not part of the proposed approach. So I just thought it could be clear initially when they were describing that. And the CVPR version of this paper does not have the appendix, maybe some issue with the publishing process. Yeah, The authors don't open source their models, but I don't know how much benefit there would be from that. So overall rating, strong accept. I really like this paper. It was novel, well motivated, state-of-the-art results, and the code is open source. Everything was great. I enjoyed reading it and I learned a lot. Conclusions, just to recap, the authors introduced this new framework. FedSM closes the generalization gap between FL and centralized training for the first time. They also did great empirical study, validate their theoretical analysis, which is very thorough, and they showed that they can avoid the client drift issue. So some future directions, like I said, I think the framework is agnostic to the task as long as it's supervised learning. So maybe they could show it on other supervised learning tasks. And also they used the 2D UNet from 2015. There have been advancements on that. So maybe seeing how more state-of-the-art models affect the performance could be interesting. My references, and yeah, thank you so much.